Hello everyone, I am Najma Nazari from the University of California, Davis. I am a member of ASIC Research Lab with the supervision of Dr. Human Homayun. This course development curriculum is funded by Intel Corporation. In this talk, I will be talk about how to migrate to DPC++. This is the third video in a series of training modules that would explain how to design hardware accelerator using DPC++ on Intel DevCloud. In this lab, we want to introduce data parallel C++. At first, we will present what is data parallel programming. Then, we will talk about where code executes in heterogeneous system. Eventually, we present data management and expressing parallelism in DPC++. In introduction part, we talk about what is data parallel programming, what are heterogeneous systems, and also we will talk about platform model. Data parallel C++ is an extension of C++ incorporating SYCL and other new features. SYCL is an industry led for adding data parallelism to C++ for heterogeneous systems. To avoid saying SYCL and DPC++ over and over, consider this. We speak of DPC++ in an inclusive manner, and all SYCL features are always DPC++ features as well. There are two approaches for parallel programming, task parallel and data parallel. In data parallel programming, data is operated on in parallel by a collection of processing elements. Each processing element is hardware capable of some computation on the data. We specify our code to work on our data in the form of a kernel. Therefore, we should focus on specifying what operations written as a kernel should apply to every data element. Data parallelism applies best on regular data structure like arrays and matrices. When we are programming in a task parallel fashion, we specify a distribution of code among processing elements and then work to have the data travel to the computation as dictated by the code. As a parallel programmer, you should use elements of both data parallel and task parallel programming. Therefore, the features of DPC++ supports both parallel programming styles. A heterogeneous system is any system which contains multiple types of computational devices. For instance, a system with both a CPU, central processing unit, often simply called a processor, and a GPU, graphics processing unit, is a heterogeneous system. Having multiple types of devices, each with different architectures and therefore different characteristics, leads to different programming and optimization needs for each device. This creates a number of challenges. Solve these challenges being the motivation behind the DPC++. The platform model used by DPC++ specifies a host that coordinates and controls the compute work that is performed on the devices. A device is an accelerator, presumably with specialized capabilities. There is always a device corresponding to the host, known as the host device. Providing this guaranteed to be available target for device code allows device code to be written assuming at least one device is available, even if it is the host itself. The choice of the device on which to run device code is under program control. It is entirely our choice as programmer if and how we want to execute code on specific devices. Note that coding in DPC++ or SYCL has a single source property. The host code and device code can exist within the same source file. Coding in DPC++ or SYCL has a single source property, which means that the host code and device code can exist within the same source file. This is illustrated in this slide. A single application may use multiple accelerators, but with a specific purpose for each. In the following figure, we consider that an application may use different algorithms that may be designed to perform on a particular type of accelerator if present. Such a program can run everywhere, and the CPU is used unless a well-suited accelerator is available for a particular algorithm. Here, we describe where code can execute, introduce when it will execute, and describe the mechanism used to control the location of execution. DPC++ applications contain C++ host code, which is executed by the CPU on which the operating system has launched the application. Host code is the backbone of the application in that it defines and controls the execution of compute on available devices. The host code orchestrates data movement and compute offload to device, but can also perform compute-intensive work itself. The host processor runs native C++ code while device runs device code. Queues are the mechanism through which host code submits work to a device for future execution. Device code executes asynchronously from the host code unless the developer explicitly ties the two together. To explore the mechanism that controls where device code executes, we can consider the following use cases. Running device code somewhere with the developer not caring which device it ends up being. Explicitly running device code on the host device, which is typically used for debugging. Dispatching device code to another accelerator device. Dispatching device code to heterogeneous set of devices. Selecting a specific device from a more general class of devices, such as a specific type of FPGA from a collection of available FPGA devices. To talk about choice of a device, even one that the implementation has selected for the user, it's important to first introduce the primary mechanism through which the program interacts with a device, the queue. A queue is an abstraction to which work is submitted for execution on a single device. A queue is bound to a single SYCL device, and that binding occurs on construction of the queue. Selection of the device is achieved through a device selector abstraction and associated device underlying selector class. SYCL defines 5 built-in selectors for the broad class of common device, as you can see in the table. Default selector, host selector, CPU selector, GPU selector, accelerator selector, and one additional selector is shipped as part of DPC++, not available in SYCL, and is available by including the header. It's Intel FPGA selector. Following figure provides an example code listing where the device with which a queue will be bound is not specified. The trivial queue constructor that doesn't take any arguments simply chooses some available device behind the scene. SYCL guarantees that at least some device will be available, which might be the SYCL host device. As we can see, multiple queues can be constructed in the DPC++ application. A fundamental concept in the DPC++ execution model is a graph of nodes. Each node in this graph contains an action to be performed on a device. The nodes have dependency edges defining when it is legal for a node's work to begin execution. The dependency edge are most commonly generated automatically from data dependencies. As we said, DPC++ applications typically contain a combination of both host code and device code. We introduce some of the basic DPC++ work dispatch construct with the goal to help you understand and identify the division between device code and the host code. A simple example is a lambda function to identify such code. A command group can be submitted to a queue, and the queue defines the device on which the work is to be performed. Within the command group, there are two categories of code. The first one, at most one call to handler class method that either dispatches work to be performed on the device code forming a kernel, or that performs a manual data movement command such as copy. The second one, host code that typically sets up dependencies defining when it is safe for the SYCL runtime to start execution of work defined in one. Right figure summarizes these methods. In the below figure, the code passed as the final argument to the parallel for member of the handler class, defined as a lambda, is the device code to be executed on a device. The parallel for in this case is the critical construct that is used to distinguish device code from the host code. We talk in this part about data management, buffers, and ordering the uses of data. Compute is nothing without data. The whole point of accelerating a computation is to produce an answer more quickly, so one of the most important aspects of data parallel computation is how they access data. Accelerator devices often have their own attached memories that cannot be directly accessed from the host. Hence, we introduce unified shared memory and the buffer abstraction for data management. We refer to access to a directly attached memory to an accelerator as local accesses. Accesses to another device's memory are remote accesses. Remote accesses tend to be slower than local accesses. Managing multiple memories can be accomplished broadly in two ways: explicitly by programmer and implicitly by the runtime. Explicitly by the programmer, after the kernel computes new results, the programmer must also copy these results back to the CPU before the host program can use that data. Implicitly by the runtime means the parallel runtime is responsible for ensuring that data is transferred to the appropriate memory before it is used. DPC++ provides three abstractions for managing memory: unified shared memory, USM, buffers, and images. USM is a pointer-based approach that should be familiar to C++ programmers. Buffers, as represented by the buffer template class, describe 1, 2, or 3-dimensional array. Buffer provides an abstract view of memory that can be accessed on either the host or a device. Buffers are not directly accessed by the programmer and are instead accessed through accessor object. Images act as a special type of buffer that provides extra functionality specific to image processing. DPC++ does not require the programmer to manage the data copies. By creating buffer and accessors, DPC++ ensures that the data is available to host and device without any programmer effort. The buffer type dimension class is generic over the element type and the number of dimensions, which can be 1, 2, or 3. To use buffer, the simplest method is to simply construct a new buffer object only passing a range that specifies the size of the buffer. However, creating a buffer in this way does not initialize its data. Buffer may not be directly accessed by the host and device. Instead, we must create accessors in order to read and write buffers. The accessor class is heavily templated. So, we typically do not directly create accessor objects. Instead, we use helper method contained in the buffer class getAccess function. When creating an accessor, we must inform the runtime how we are going to use it, and we do this by specifying an access mode. Access modes are defined in the table, as you can see. In the code example shown in below, the accessor myAccessor is created with access mode read-write. This lets the runtime know that we intend to both read and write to the buffer through myAccessors. In DPC++, kernels can be viewed as asynchronous tasks that are submitted for execution. In many cases, kernel must execute in a specific order so that the correct result is computed. If obtaining the correct result required task A to execute before task B, we say that a dependence exists between task A and B. In DPC++, we can express these dependencies through event object. First, we can synchronize through the host by explicitly calling the wait function method on the event. This forces the runtime to wait for the tasks that generated the event to finish executing before host program execution may continue. The second way is to use method named depends-on function. This method accepts either a single event or a vector of events and informs the runtime that the command group being submitted requires the specific event to complete before the specific task may execute. This figure shows an example of how depends-on may be used to order tasks. Implicit dependencies between tasks in DPC++ are created from data dependencies as shown in this table. In this figure, we execute three kernels, compute B, read A, and compute C. Then read the final result back on the host. The first decision to make is whether you want to use explicit or implicit data movement, since this greatly affects what needs to be done to bring a program into DPC++. Implicit data movement is generally an easier place to start because DPC++ will handle all the data movement, letting you focus on expressing the computation. We have already covered how to control where code runs on what devices and how to get data to our code accessible from a particular devices. Now we introduce the concept of data parallel kernel. Kernel describes parallelism in terms of abstract concept that an implementation, for example, a combination of compiler and runtime, can then map to the hardware parallelism available on a particular target device. It ensures that applications can scale up or down to fit the capabilities of different platforms. A parallel kernel is not a loop and does not have iteration as shown in this slide. Rather, a kernel describes a single operation which can be instantiated many times and applied to different input data. When a kernel is launched in parallel, multiple instances of that operation are executed simultaneously. DPC++ provide 3 different kernel forms, each with their own execution model and syntax. The first form is used for basic data parallel kernels. The second kernel form extends basic kernels to provide access to low-level performance tuning features. This second form is known as ND-dimensional range. The third form is referred to a hierarchical data parallel, referring to a hierarchy of nested kernel constructs that appear in source code. The most basic form of parallel kernel in DPC++ is appropriate for operations that can be applied to every piece of data completely independently and in any order. Basic data parallel kernels are expressed using the parallel for function. The function only takes 2 arguments. The first is a range specifying the number of items to launch in each dimension, and the second is a kernel function to be executed for each index in the range. The kernel can take either an ID or an item as its argument. Like basic data parallel kernels, ND-range kernels are written in a SPMD style where all work items execute the same kernel program applied to multiple pieces of data. The key difference is that each program instance can query its position within the group that contains it and can access additional functionality specific to each type of groups. Work items represent the individual instances of a kernel function. The work items in an ND range are organized into work groups. Work groups can execute in any order, and work items in different work groups cannot communicate and synchronize with each other except by way of atomic memory operation to global memory. Diagram in this slide shows how the work in this kernel is mapped to work item in each work group. Grouping our work items in this way ensures locality of access and hopefully improves cache hit rates. For example, the work group has a local range of 4,4 and contains 16 work items, but only accesses 4 times as much data as a single work item. In other words, each value we load from memory can be reused 4 times. Hierarchical data parallel kernels offer an experiment alternative syntax for expressing kernel in terms of work groups and work items, where each level of the hierarchy is programmed using a nested invocation of the parallel for function. One complexity of hierarchical kernel is that each nested invocation of parallel for creates a separate SPMD context. Each scope defines a new program that should be executed by all parallel workers associated with that scope. Mapping nested parallelism to accelerators is a challenge that is not unique to DPC++. As shown in this slide, kernels expressed using hierarchical parallelism are very similar to ND-range kernels. We should therefore view hierarchical parallelism primarily as a productivity feature. It doesn't expose any functionality that isn't already exposed via ND-range kernels. But it may improve the readability of our code and or reduce the amount of code that we have to write. Choosing between the different kernel forms is largely a matter of personal preference. However, the rule of thumb is the flowchart shown in this slide, which select a kernel from based on whether you have previous experience with parallel programming, whether you are writing a new code from scratch or are porting an existing parallel program written in a different language, whether your kernel is embarrassingly parallel, already contains nested parallelism, or reuse data between different instances of the kernel function, whether you are writing a new kernel in SYCL to maximize performance, to improve the portability of your code, or because it provides a more productive means of expressing parallelism than lower level language. Now, let's look at a simple vector addition in the PC++. At the beginning, we should create a queue. We do not select at any specific device. Therefore, it will run on a host CPU. After that, we should create buffers for data management between the accelerator and host. We must submit the queue. Then, in order to use the buffers, we require to define accessors, as you can see in this slide. Then we use a dispatch function parallel for, as you can see in the step 5. And finally, inside parallel for kernel, we put the computation and it will be executed on the accelerator devices. The final step is step 6. Thank you for watching. I encourage you to follow up with other videos, and there will be also a GitHub repository that provides all the codes.